a little bit about how me and my colleagues at DKFZ, how we're trying to sort of go towards transforming healthcare with general purpose AI. And first of all, I would like to convince all of you that we have, or we're facing a real problem in our healthcare systems now already, and even more so in the future, because we're facing an imminent data explosion in healthcare. So already 30% of the world's data volume today is generated in the healthcare industry, and it's the sector with the highest growth rate, right? 36% per year. And this immense data explosion is driven by different factors. For one, data acquisition techniques are becoming much more cheaper, like genomic sequencing or lightweight MRI protocols and so on. Also, we have aging societies, right? So the demand for this kind of data collection is rising every year. And also we have globally seen a better access to medical care around the world, right? So this is how this data flood is motivated. At the same time, you can imagine the human capabilities of analyzing and processing all this data and making sense of it is really limited. So a study found that already today between 30 or 50% physicians are thought to be affected by burnout. I think this shows the immense pressure that's already on our healthcare systems today, and that will increase in the future, right? And so because my background is in medical imaging, so all the points that I'm making are sort of generally applicable to AI and healthcare, but because most of the examples that I'm going to show are about medical images, just want to make the point here how important these images are in this context. So they make up 90% of this data that I talked about, and also a study found, like, if we get the imaging right, if there was imaging everywhere available where it's needed, we could save already 10 million lives from cancer deaths in the next years, right? So I hope I convinced you that we really need an AI-driven transformation of healthcare to be able to cope with this imminent data flood. Okay, so let's look at how we're doing today. What's the current status of integrating AI into the clinics? And the current approach is sort of like, for each new task, we are training a specialist model to solve this task, right? So for each new task, we need to label lots of training data for the new task, and then also configure the model. That means tuning it sort of to really perform well on the task, right? And with this kind of approach, how far do we get? Well, there are already almost 700 AI-enabled medical devices that are FDA approved. And again, making the point that 77% of those are in radiology to show how important these images are. Okay, so this number, 700, doesn't sound so bad, right? So does this get us where we need to go to transform healthcare? That's the question, and so my clear answer to this is no. And I want to highlight a few different challenges that we will face, or that we're facing with this approach of training specialist models for each task. Right, so for one, we have an extreme diversity of clinical disorders and data shifts in the medical domain. So again, just an example of radiology, there's around 20,000 different disorders in the catalog of radiology, and around half of them are in the so-called long tail of the distribution of rare diseases, right? So it will be extremely difficult to get enough training data for each of these very rare tasks. I remember I had a colleague during my PhD sitting next to me. His task was to write a deep learning model to detect a rare bone cancer. And even after 3 years and multiple clinical collaborations, his data set consisted of 7 patients. So just to give you an intuition what it means to have a rare disease and trying to model that with AI, right? But okay, let's assume we get enough training data for each of these sort of tasks. Then we would still need to account for the immense data variations that we have in the medical domain. That means when you apply this algorithm in the real world, the data changes, right? You have population characteristics that are changing, age, race, sex. You have scanner variations, and so on. And if you don't account for this in your training data, then your model will be biased and will not be reliably, robustly performing in action. There's a really impressive study that shows how problematic this can be. So this is a meta-study that after the pandemic analyzed 62 different AI models that had been proposed to detect COVID-19 from chest x-rays, right? And the study found that none of these 62 models had any potential for clinical use. They were all flawed. And the biggest issue was a bias. And so the most prominent bias was that people had, for the healthy patients in their training set, they were made of kids, so chest x-rays from kids, and the disease, like COVID-19 examples, were from grown-ups, so the model was just learning to differentiate between kids and grown-ups and not really to detect COVID-19. So that's what happens when you don't curate your training data to account for these data variations, right? So it's even more complicated. Okay, but now let's assume we're also solving this problem. We collect enough training data and all the necessary variety for all these tasks. We would still run into the problem, the immense bottleneck that we need ground truth information to train these specialist systems, right? The main problem in medicine is that we often don't have the true biological information, right? You can't, for every patient, do a biopsy and peek in with a needle and really do a biological analysis of the tissue to see what it is, right? So what we're mostly relying on is the radiologist's guess based on the image itself. They draw in references, here's the tumor or here's this structure, and we need to rely on that. And that's a very noisy process. You can see here as a tumor that's been outlined by different radiologists for subsequent radiation therapy. So you really want to know where the contour is for this process. And you can see how noisy this is, right? So you actually would want to get multiple raters' opinions to account for this uncertainty also in your training data. Right, let's shift gears a little bit. Another important problem is really the human adaptation of these systems, right? We saw 700 FDA-approved devices, and this is how they're actually used in practice. So we see here on the upper, let's say, can you see this? My cursor? No. On the upper left plot, you see that it's only a handful of really use cases that are actually used. So the point is, just because a system works and is FDA approved doesn't mean it's really useful in clinics, right? It doesn't mean that it really improves the workflow of a human doctor, right? So that's also something that we need to account for here. And another aspect of this is the so-called automation bias. So a study found that an AI opinion can also negatively affect the performance of a radiologist. So even, the study found that especially younger and more inexperienced radiologists are prone to sort of relying on the AI when it's wrong, right? Okay, and the last problem that I want to raise is a bit of a more general sort of meta topic, and it describes a general discrepancy between the research that we do and what is actually landing effectively in the clinic and has impact, right? This issue is also sometimes called the AI chasm or like the translation gap. I think the COVID example we saw is a really good example for this. Lots of research is being done, but it's not really clinically useful, right? So we need to be more efficient in the research that we do as well. Right, now for each of these problems you can sort of generate a research question that we need to address and solve in order to achieve this clinical AI integration that we need at the scale that we need, right? And so in the talk now I want to highlight some publications of the work that I did together with my colleagues in the last 3-4 years where we address these questions, right? And then lastly, in the last chapter, I want to talk about sort of the new paradigm of foundation models and what this means for the questions that I want to answer and the research that I showed you, right? Right, so let's dive into it. But before I show you these work examples, I want to make clear that none of this has been done by myself, but there's an awesome team behind all of this. So in the first row, that's my team that I'm managing. And then we have my faculty colleagues at DKFZ, so Fabian Isensee, Klaus Meyer-Hein, Lena Meyer-Hein, and of course the clinical partners that are very important. Okay, so let's dive right into it. How to generalize models across tasks. So how can we develop models that do not fall into sort of this need to tune and collect data for each new task, right, that we saw with the specialist models. And I want to show you something that we did in the last 3 years where we specifically tackle the problem of having to tune and configure your model on each new task. So I'm sure you're all familiar with this because Freiburg is sort of the capital of AutoML, right? So I don't need to tell you what hyperparameter tuning is. I just want to make the point that it's maybe even more complicated or complex in the medical domain because the data is very large and complex. So we typically patch the data and only show the models crops of the images during training. So you have an extra layer of complexity in engineering because you need to decide how large is the patch size, how do I sample these patches from images and so on. Also the diversity between data sets is very large. So you really need to fine-tune every hyperparameter again when you shift your data set, right? Maybe it doesn't matter between Cypher 10 and ImageNet, but it matters between a brain MRI and a chest CT, right? Okay, so you see here it's a very complex trial and error process that every PhD student on each new project sort of needs to go through. Also, we have very long training times, 3 to 5 days with a large model in this 3D domain. And then it's a very slow and really annoying process, right? And yeah, this process has really bad consequences for research. Like, not only does it bar access to many users like clinicians because you need expert knowledge to do this right, yeah, but it also like leads to that you cannot take care of your baselines very well, right? It's hard enough to get your method working, but then you want to compare against 4 baselines on your new data set, but you don't have the time and budget to go through the same optimization process. And then we have a really big problem in our research field with very flawed baselines, where your baselines are just not well configured. And then half of the papers are like, yeah, run into the problem of, does the method really work, or where the baseline is just not well configured, right? Okay, so we introduced NNUnit to tackle this. So NNUnit is a general purpose AI in the sense that it adapts itself to each new task automatically, right? So you don't have to do this manual tuning process anymore. And this is how it works. So you have the entire sort of segmentation pipeline, deep learning pipeline that is configured. So you can really use it out of the box then without any expert knowledge. And so this is the first step here. We identify fixed parameters. So those are the hyperparameters that we don't need to adapt between data sets. You can just leave them fixed. This is what we found in lots of empirical experiments, right? And then we have a fingerprinting process where NNUnit scans a new data set and extracts sort of the key characteristics of this data set. And this information triggers a cascade of sort of rules. This is a rule system, right? Sort of if-else statements, and they then adjust the hyperparameters that are interdependent. Like, let's say if the batch size fits into the memory, then you can turn up your patch size a little bit more, have a larger crop from the image. And so there can be also iterations to check if a different setting fits into GPU memory, and then you sort of increase your numbers again and so on. So this is executed in a few seconds or 1 minute, right? And then you have an adjusted configuration system based on the data. It all happens automatically. And with that, we train 3 different unit architectures. Since Freiburg is also home of the unit, I don't need to explain you what that is. And really only the last parameters, like which of these 3 architectures to select and so on, is then learned from the data empirically out of the training, right? And just to say how this compares to AutoML, in AutoML we would need to learn all these parameters from the data. And you can imagine that this takes a lot of time. It's a very high dimensional optimization problem. You need a lot of training data for that and a lot of compute, and this doesn't really scale to our medical applications where we don't have a lot of training data and a lot of compute, or it's already very complex, right? So you can see it as a shortcut to AutoML, where you're trying to sort of put in heuristics, put in domain knowledge as much as you can, to not having to learn these parameters from the data, right? But put in your human knowledge to take shortcuts, right? And again, important, we don't claim that these configurations that come out of this are perfect, right? You can see it as a good starting point. If you feel like you want to tune these 2 or 3 hyperparameters that you're not happy with to win a sort of competition or something, then that's a very good idea. We do that as well, but it's a good starting point. And so this is how well it works. Here you see only out-of-the-box performance, no further tuning from our side. So each of these 53 panels is one international task, competition, challenge. The red dot is NNUnit, higher is better, and each blue dot is a competing team. And you can see that NNUnit comes out on top in 33 out of these tasks, and on the other ones it's also like on par or in the range of the best solutions. And to give you an intuition of how sort of surprising this is, you wouldn't expect a decathlon athlete to beat the specialist athletes in their respective discipline, right? But this is sort of what happens here, because NNUnit is not manually tuned or touched at all on these competitions, and it competes against manually tuned solutions. So it works really well. And this, what's important here is to have a clean, also train test split, right? But because we claim generalization across data sets, you also need this on a meta level. So the point I want to make here is that the now tasks that are now highlighted in yellow, these we used for development of this auto configuration system. And then the ones that are not highlighted here, we just applied it out of the box without having ever seen these data sets before, right? So you need like a clean train test split, but on a meta data set level. Right, and then this gives you an idea of what it can do. So basically any medical image, 2D, 3D, or structure up to the cell level can be segmented out of the box with this model. It had quite an impact on the field, measured in citations and so on, and it's also been adapted really well. Like now it's used by 9 out of 10 winners in the different challenges, even in the same year that it was published. And so on. And Olaf Fronnenberger, who's from Heidelberg, he also really liked it, the creator of the unit. I'm showing this, of course, it's a bit of a bragging slide, but I want to make the point, what I think is nice about it is that you can have real impact on the field without jumping on the latest buzzword train, right? NN in this NN unit word stands for no new. So we really want to make the point here that you don't need the newest fancy architecture where you put in new attention layers and so on. Just do a solid work of engineering and get things to work right, in a modest way, and you can still have very good impact and people will see that it works. That's sort of the message here. And then we wanted to see if the same principle works in other domains than semantic segmentation. So next we tried it for object detection. So this is 3D medical object detection. And the method behind it, we called it NN detection. I know it's not very original. The challenge here was to extend the auto configuration system to the higher complexity of object detection methods, right? You have all these anchor systems in there that you need to also automatically configure. And we could also show on a large number of data sets that it works better than the NN unit baseline. Right, now let's take a step back a little bit and abstract from what we did here. Because when we can abstract the recipe and the method behind this, we can apply it to other areas, right? So what we did is, for like a series of custom problems, we extract the key characteristic of this problem, and then we call that fingerprint. And then we have sort of a generalizing solution that operates in this fingerprinting space. In our case, it was this rule-based system that then executes some rules and creates, in an instant, very customized, specialized solutions, right, for each problem. And so now we saw how we applied this to method configuration, but we're also going to see how we apply the same principle to different topics like data annotation or even evaluation metrics. Okay, let's go to the second question. How can we overcome the annotation bottlenecks? So the manual effort of annotating this training data that is especially cumbersome also in the medical domain. And let's take NN unit again as a starting point here. So I hope I convinced you that we, to a certain extent, solved the problem of having to configure our method to each new problem. But what NN unit does not solve is we still need the training labels. So we still need to train each task from scratch, right? And that's, of course, also still a large bottleneck. So Fabian, my colleague, who actually was the technical lead of NN unit, so all the engineering credits go to him, and he's now running a service lab where researchers from all of Helmholtz, so all the different Helmholtz centers, can come with their problems and ask Fabian and his team to help them with their image analysis. So many people come with their data set and want their data set labeled by NN unit, right? And then it's always the same problem, well, we don't have training data. Okay, and so the kind of work mode that Fabian and his team converge to is something like a human active learning loop, right? So they start to train in a unit on a small starting budget, and then they predict the entire data set, and then a human like Fabian or someone from his team goes through all the NN unit predictions in the entire data set and looks for errors, and then feeds back these samples with the errors to the annotator or like the customer, for the next annotation round, and then we train NN unit again and so on, right? And so this is good for the annotator and the customer because they only have to annotate the most informative already selected samples, which is good for them. But you can imagine that it's a high burden for the human and has to look for errors, and it doesn't really scale to larger data sets, and we live in a time where data sets get larger and larger. So me and my team now try to help out and automate this process by an active learning model called NN-Active. It's sort of an active learning wrapper around NN-Unit, where we want to automatically find these errors, right? And so to make this clear, it's not only like active learning for segmentation project, but it's more ambitious because we want to maintain the out-of-the-box functionality of NN-Unit. So this auto-configuration, we need to extend it now to this active learning wrapper, right? And that's the ambitious part of it. And you can imagine that we want to use the same recipe here of this task fingerprinting again for the active learning wrapper. Since this is a very ambitious project, we found that there are two fundamental research questions that we need to address first in sort of two preparatory studies on our way to this NN-Active method. And the first one, which was presented at NeurIPS last year, is does active learning actually work? And this is indeed an open question, so you wonder about this maybe, but there's really sort of half of the research field says active learning doesn't work and just do self-supervised or semi-supervised learning instead. And the other half just keeps on proposing new active learning methods and says, see, my method works better than the baseline and so on. So we wanted to know what's going on there in this very inconsistent literature landscape. And we relate this inconsistency to 5 key pitfalls in how people evaluate their methods, right? And these pitfalls, they range from neglecting important design choices like the starting budget or the data distribution, to also having, again, not well configured underlying classifiers in their methods and their baselines, but also a lack of comparison against alternatives like self-supervised and semi-supervised learning. And you can see in the literature here that all of these recent studies are subject to several of these pitfalls. So what we did is a large empirical study. So first we propose a protocol, a meaningful and standardized evaluation protocol for active learning that avoids all these pitfalls. And then we did a large empirical study where we test all existing methods under these meaningful conditions to really deduct meaningful insights and sort of create a new level playing field for active learning community to see where we really stand. And I'm going to jump over the detailed results tables and experiments and just jump right to the main insights that we drew from all these experiments. And first of all, and maybe most concerning, is that the active learning methods in literature, they are substantially sort of flawed by subpar classifier configurations. So we could show that just if we tune our classifier nicely, like if we care about the best learning rate and so on, we can beat most of the literature methods with a random baseline. So a baseline that only samples the next data samples in a random manner, right? And that's concerning. But we could also show that with a lightweight configuration protocol, if we install this, we can then reinstall the active learning performance and show that it works better if you configure your method well. We also saw, maybe not surprising, that active learning generally works really well in class imbalance settings. There's one method called batch that was best performing across all these experiments that we did, so in a very robust manner. So if you do active learning, you should have a look at this method. And also we found that, for example, combining active learning with self-supervised learning works really well in terms of performance, but also the two are just a very good fit, because the problem with active learning is often the training times, right? You need to do your training 10 times. But if you do this based on self-supervised learning, you only have to do maybe some lightweight fine-tuning, and that sort of decreases this burden of training time. What we also found, it's not compatible really with semi-supervised learning. Okay, the second question that we needed to answer on our way sort of to NN-Active is how to get useful uncertainty estimates from the segmentation method, right? Because we need these uncertainty estimates to do active learning. And this was presented at ICLR this year. And so again, we built a systematic framework for evaluation because we found a very inconsistent literature landscape. And in the first part of this framework that we proposed, we want to really control for different uncertainty types. So there's aleatoric uncertainty, that's the data inherent uncertainty, right? let's say you have an ear of an animal behind a couch and you don't really know if that's a cat or a dog, then it doesn't matter if you get 50 more images of this, you will never find out if it's a cat or dog, right? You just don't have enough evidence in the image for your target. So that's the data inherent uncertainty. And then you have epistemic uncertainty, which is more sort of the model uncertainty that you can fix by feeding it more data. So let's say there's a new subtype of a gorilla. At the beginning, the model will be confused if it's a gorilla when it sees it for the first time, but when you have more training labels, then it will figure it out, right? That's epistemic uncertainty. And sort of the community, the research field, often, so most studies are based on the assumption that this separation works and that it's important. And we were not convinced and wanted to also challenge this, right? Does it really work in practice or only in theory, and is it really important? For example, there's two very highly cited studies that are based on the assumption that test time augmentation models aleatoric uncertainty. And this doesn't really make sense if you think about it. You have this ear behind the couch, right? And if you now rotate this image, it will not give you more information about how much noise is in that image. But because the evaluation in these studies, again, was flawed or sort of not rigorous enough, they didn't control for these different types and factors, it went unnoticed that the assumption is wrong, that the basis sort of that the paper builds on, right? And so that shows that we really need this controlled environment. In the second part, we're ablating each component of the segmentation, of the uncertainty method specifically, right, to avoid wrong credit assignment. For example, we see studies that claim my uncertainty method works better, and then it turned out that the only thing that worked better was the aggregation stage in the end, where you aggregate from pixel level scores to image level scores, right? So we need to look at each component individually to figure out where the gains come from. And the last part is also based on an observation that we make, that uncertainty research is often a little bit has the notion of some self-purpose, right? We do uncertainties to research uncertainties, and we make the claim that we should always connect an uncertainty method with a concrete purpose, right? Because the quality of this method only shows in a concrete purpose or downstream task. And so we test existing methods on 5 concrete downstream tasks to really show what works where and so on, so that users in the future know what's going on, right? And so again, I'm gonna skip the detailed results and just give you the most interesting insights. So we found that separating these two uncertainty types, it works well in theory and in toy settings, but not so much when you translate it to real world data. It's just too noisy, there's too many factors coming into play, and you cannot clearly separate these two types anymore, right? It can be helpful though, because we were also wondering if it makes even sense to separate them. So for active learning and OD detection, it can be helpful to separate them. That's what we found. We found that deep ensembles show the most robust performance across all downstream tasks. Maybe that's not surprising, but deep ensembles is also a very expensive method, right? Because you need to have different models and trainings. So we found that test time augmentation actually models epistemic uncertainty. This is a bit now controversial because it directly contradicts the two highly cited papers I showed you before that are based on the assumption that it models the opposite, right? And now we empirically for the first time could show evidence that it actually models epistemic uncertainty, and it's actually a good light world alternative to ensembling. Yeah. Right, and so now equipped with this knowledge about active learning and uncertainties, we're currently building this active learning model. Here are some very preliminary results for an active model, and now you can see here the x-axis is the different training stages of active learning, where you have more labels every time, and we want to beat this random sampling baseline, right? And so yeah, there's more to come here in this area. Okay, let's shift gears a little bit for the third question. How can we really enable reliable clinical decisions, right? Because in the end, the liability of clinical decisions will remain with the human. So AI is only useful if it can be reliable, right? If the human can rely on it, otherwise they will not use it. And so how can we make this work? Because AI methods often come with the sort of promise of full automation, right? You put your data in, you press the red button, out comes your result. I don't know, breast cancer detection. But what if your breast cancer detection algorithm has 97% accuracy? What do you do with the failure cases, the 3%? You cannot just say, well, bad luck, because that's not acceptable in high-stake applications like clinics. So what happens is that the human still needs to monitor all the outputs and check for failure cases, right? And then the question is, what's the purpose of the AI after all if the human still needs to check each image? And so what's often proposed here to have a more efficient and symbiotic collaboration between human and machine are these deferral systems where the prediction model or classifier, together with the prediction, outputs a confidence score. And then based on this confidence score, you can put a threshold and say if the confidence is at least 80%, I trust the model, I don't need to check it, and then you only revise the cases that are low confidence. And it's important, in this definition, confidence score can be really anything that is a continuous score that you can threshold, right? We also include here OOD detection scores that come from a density estimator, or learn scores from extra networks, or directly uncertainties that are directly abstracted from the softmax distribution and so on. Right, and so now it's important from a technical perspective, there's now two tasks here for this failure detection system. So one, you can prevent failures in the first place by just not making anything wrong, right? 100% accuracy, all fine. But in the second task now, you can detect the remaining failures based on this confidence score. And so when I started the group 3 years ago, I wanted to build such a system for the clinics, and this is the literature landscape again that I found. So you can see the first task of preventing failures. Here we have a very nice and consistent research landscape. So we call this, you can see that a very important aspect of evaluating failure detection is the distribution shifts, right, between training and test data, because they are a main source of failure, and we want to evaluate failure detection methods. So we distinguish here between IID, test sets, covariate shifts, so those are shifts where the label is preserved, let's say a new subtype of a tumor, but it's still a class that the model has seen during training, and then new class shifts, like, I don't know, suddenly a house number showing up in an animal classification or something. Right, and you can see, in task one, we call this testing the robustness of the classifier, right? How good is the accuracy under these shifts? And it's all good, there are lots of benchmarks, lots of different distribution shifts. And then we go to the second task and we find a very scattered landscape. You can see 4 different research fields that have historically grown to be separated and siloed. For example, OOD detection, and so these fields don't really cross-compare their methods, and you can also see they don't really test their methods under a lot of distribution shifts. And let's look at OOD detection as an example, because this is a very prominent research field. And I think it's really interesting that most of the papers currently, they really claim that the main purpose of the methods that they propose is to detect failures of a classifier that exists, right? And so the question that we're asking is, well, if you want to have a method that detects failures of a classifier, then why don't you evaluate it also that way? Because what they do is they introduce an outlier label that only distinguishes between outliers and inliers, right? And this is sort of the assumption that all outliers are failures and will be wrongly processed, and all inliers are okay, they can be processed by the model. But this is a very flawed assumption, right? And the question is, why do we make this flawed assumption if we have the actual information of the classifier and can just check where it fails? So this plot here visualizes it a little bit, what I'm trying to say. This is what we want to do with the failure detection method, right? We want to accept all correct predictions in our confidence. We want a high confidence for that. And we want to reject all the failures. And there's different types of failures. Inlier can be failure. We have covariate shifts that can be failures. And we have new class shifts that are failures by definition, of course, because the class cannot be, has not been seen before, cannot be predicted. And this is what the outlier label does that we used in all this research. It says that inlier misclassifications are okay because they're inliers. It has no idea about what to do with covariate shifts because we cannot really tell if it's an outlier or not. So saying inlier outlier is sort of an artificial discretization of something that is actually a continuous spectrum, right? When does something start to be an outlier? And in the covariate shift, you could argue those are the most important shifts. You wouldn't expect in an MRI scan to suddenly an image of a house number to show up, right? But we expect very subtle shifts, like a new pathological subvariation or something like that. So yeah, my point is that this outlier label is really flawed. And so what we do in the study is to unify all these separated fields under, again, a unified evaluation protocol that really reflects this task of failure detection. And then for the first time, we can compare all these methods from different fields under the real sort of task and the real metric, and under lots of realistic data sheets. Again, jumping to the main insights that we find here, and again, very concerning that none of these evaluated methods from literature was actually able to beat a simple softmax baseline. So you just take the highest probability of your softmax vector, and that's your confidence score. This was sort of the most robust method, and that's again very concerning. We also tested OD detection sort of for the first time under covariate shifts, right? Because with the outlier label before, you couldn't really test that. And we found that most of these OD detection methods, they work really well on the far OD setting. So house number showing up in a cat versus dog task, but not with actual realistic shifts. We also found that the metric that we proposed works well. And that's sort of it. And then in a follow-up project that was presented at MICCAI last year, we extended this study to the biomedical domain, and we also found here that the ratio of silent failures, so failures that are not detected by confidence scoring, is really high, and that's concerning, I think, for medical applications. So we built this tool that you can see here where you can directly check where your undetected failures come from. So this shows you the latent space of a classifier, and we colorize sort of the confidence scores as well as sort of the distribution shifts and so on. And then you can hover over this latent space and directly check which images correspond to that and so on. Right, this is the last question. It's, as I said, a bit of a meta topic that addresses generally sort of the gap between research and application, right? How can we make sure our research is really clinically relevant in this domain? And we saw already impressive examples of this gap with the COVID study that I showed before. But another aspect of this gap is evaluation metrics. Because if you think about it, the metric defines the task that you're trying to solve, and so it sort of simulates the application that the model should do later. So it's really the glue between your research and the application is this metric, right? So we should make sure that we choose the right metric and the right glue. And so here's an example for what can go wrong with metric selection. In the biomedical domain, the most addressed deep learning task is semantic segmentation. Over 70% of international competitions in this domain are segmentation. The study here also found that the dice coefficient, so just measuring the overlap on a pixel level between structures, is the most used metric. So let's see a typical segmentation example and how this metric behaves. On the left, you can see the reference, or the sort of ground truth that we want to segment, and then you have two competing models on the right with their respective predictions. And you can see that the dice score prefers the orange model, right? But you could argue that clinically it's often much more relevant to detect all structures, right? For example, in cancer research, it's very important to detect metastasis and like the lesion load rather than having the contour of a large tumor perfectly outlined, right? So we are using the wrong metric here to assess this problem, and this problem should have rather been sort of phrased as an object detection or instant segmentation problem with a respective metric. And so we saw lots of these pitfalls also in our domain, and so 3 years ago we started the Metrics Reloaded initiative. We sort of recruited over 70 international experts. My colleague Lena Meyer-Hein was leading this. And to converge sort of as a community on good recommendations for metrics, right? So, and this now was published a few months ago in two sister publications in Nature Methods, where in the first we just visualize and highlight all the pitfalls that we found. So I showed you one of them, but in the paper we have around 100 metrics and around 35 pitfall categories. And then in the second study, we want to solve this problem. And so what we do is we created a recommendation system where users answer questions about what they want to do with their problem, and then in the end it goes like to some decision trees, and in the end you get a recommendation of good metrics for your problem, right? And that's the Metrics Reloaded tool. And you can imagine that this decision tree, like an asking questions about the problem, is exactly this fingerprinting principle that I showed before, right? By asking questions to the users about their problem, we're extracting the fingerprint from their custom problem, and then we have our decision trees, our rule systems that then map from their custom problem to a good set of evaluation metrics. This is the scope of the project. So we are tackling all like classifications at all scales, from pixel level to image level, and it's sort of domain agnostic, at least in the medical domain. Right, and then this is how sort of the framework looks. Each of these panels is sort of has a sub view with the respective decision tree. You can see there's a trajectory that you go through different metric categories that you can collect, and so on. Let's look at one example. This is the beginning where you first get defined what type of task your problem is. Is it a segmentation problem? Is it an object detection problem or classification problem? This is what a decision tree looks like, right? You answer questions about your problem. And so the pitfall that I showed before about the die score wouldn't have happened because you would have landed here at instant segmentation also. Right, and so because both papers have 200 pages each, we also created this interactive online tool, so you can check out this webpage and then you only click through. With a couple of clicks you can like get your metric recommendation. You don't have to read the whole paper. And yeah, so this took much longer than we expected, and it was really a lot of effort. So we were very relieved when the papers were accepted, as you can see here in this slow motion GIF. And also the editor that was handling this was saying really nice words about our paper, which was really nice after so much work. Okay, I will have 5 more minutes if that's okay. Everyone's still awake. I would like to talk in the last chapter a little bit about what all of what I said means now for sort of the new AI, right? We've seen CNNs now, we've seen specialist models and so on. But the AI that we've seen in the last 1 or 2 years is very different, right? We have foundation models, we have language models, and so how does all the research that I showed you translate to this new era, and how can foundation models and this new paradigm of AI help us to solve the questions that I raised? And so this is a Nature Perspective article from last year. You may have seen this, how people imagine foundation models to be integrated in the clinic in the future, right? So here everything is perfect. You have all available information about a patient, right? All different data modalities are just thrown into this one model, and it can be adapted to all the different downstream tasks that you need. It has perfect language understanding, so you can interact with it and exchange information. And so let's see how the research that I showed you sort of can help to develop this vision and to get closer to this vision. First of all, I talked a lot about the task fingerprinting, like with NNUnit. And so what we're currently working on is to shift this to the fine-tuning stage of a foundation model, right? Because here as well, let's say users in the future, they're not training models from scratch anymore on their data. They will download a foundation model and then just fine-tune it, right? And there again, you want a standardized sort of auto-config process. There's different fine-tuning methods out there, different hyperparameters to be tuned, and we're working on sort of doing an NN version of this. Active learning as well, I think, will be very useful. I think we will see a renaissance of active learning here because let's say you have a data set of 10,000 images, and the whole point of a foundation model is that you don't need to label all of them anymore. You only need to label 200 of them because you only need to fine-tune, right? And so the question will be, which of your 10,000 images shall be the 200 that you label and that you fine-tune on? And that's again an active learning problem, because you want to select the most informative images. That the ones that you label should be very representative of the data, right? Active learning can also be very useful, I think, in a self-supervised foundation model training itself. In the medical domain, we haven't really seen any convincing foundation model, at least in 3D. I think this is because we have this very low signal-to-noise ratio in the data, right? So we're often looking for needles in the haystack, a small tumor in a large 3D MRI body. How do you tell the model where to look without having any labels, right? And so I think we will need very smart sampling strategies. And there's a nice paper from DeepMind where they do sort of online active learning and online rank regions of images and images by their informativeness and then show them to the model during training. I think this can be interesting. Failure detection that I talked about, I mean, now in the future we will have language to interact with the model, right? But I think we will still need this failure detection and to validate for failure detection under the same protocol, right? Even if the modality now is language. And I think in times now where these models are trained on internet scale data, it's even less useful to talk about outliers and inliers, right? I often wonder when we see, for example, out of distribution papers on CLIP or zero-shot generalization from CLIP, how do you even make sure that the data wasn't in the training set, right? What's an outlier for a model that has seen everything? So just one more reason why we should talk about failures and not outliers. Right, and yeah, maybe the most important point is that we really need to have very crisp task definitions. What do we want this model to do concretely in the clinic? I think we need to define this first before starting building these things, right? Because, for example, my friend works in the, it's also Jörg's friend, works at the AlphaFold team, or used to work there, and I asked him what was the most important reason for AlphaFold to work so well, and he said it was the metric and the benchmark. So they had a clear metric that they wanted to optimize, and so they had internal leaderboards where they knew if the metric is 1% better, our model is better, right? And so you need a clear defined task to guide the development process. That's my point here. So we need to think about this first, and one way to think about this design problems that we have is the spectrum of generalist versus specialist, right? During the talk I said we need generalist models, generalist purpose AI models, but maybe the best solution lies somewhere in the middle, right? It's a spectrum where on the one side you have specialists for each task, on the other side you have one model that solves all the tasks, and maybe, I don't know, the solution is to have like a hierarchy of models where a generalist can access different specialists or something like this, right? Another way to think about this is we see a lot of different adaptation schemes flying around. Do we need zero-shot generalization, or do we fine-tune, and so on? And we need to think about which sort of generalization gap do we actually want to get over in the clinics, right? Do we expect just on application new data from a new scanner to appear that we want to generalize to? Maybe then zero-shot generalization is enough, but do we want to apply it to a whole new task and data set and body region? Then maybe we need to fine-tune and so on. So these are design decisions and very open research questions that we need to think about. Right. Very finally, I want to show you what we are doing in this domain and the foundation model that we are building. So I'm part of this Helmholtz think tank where we were thinking about how can we bring foundation models into all of Helmholtz research, right? This is not only medical, this is also GeoMA and DLR and so on. And so we wrote up this concept that ended up being a large project call, and now 4 pilot projects have been selected from different areas. Climate is in there, energy is in there, and there's also one foundation model from health in there, and I know it's also a bit fishy, but I'm also the PI handling this selected project, but I had nothing to do with the selection process. And so our foundation model, we call it the Human Radiome Project, and just give you a quick overview of what we're doing right now. I said already, NNUnit is a good starting point, but we still have the problem that we need to train each task from scratch, right? And then need the training labels. And this is what we want to solve with this foundation model. So we're currently collecting a very large data set of almost 5 million 3D volumes. So this is MRI, CT scans, and so on. This is an immense data set that exceeds the currently largest data sets by a factor of 40. So just collecting it, building the infrastructure for it, and so on is a huge challenge at the moment. Then we want to train this in Jülich at the supercomputer in a self-supervised way, and then we have sort of this foundation, right? This representation that's sort of, we hope, gives us a fundamental understanding of human anatomy, and we can then fine-tune this to a lot of different downstream tasks that we collected. Right, and maybe one question that comes to your head is like, okay, NNUnit is all nice and good, but it's a CNN, and CNNs are very old school, right? So shouldn't we use a big-ass transformer for this? And so we kind of benchmarked all the methods for medical segmentation a few months ago. This will be presented at MICCAI this year. And we found out that CNNs still come out on top, right? Again, we relate this to pitfalls in validation. So there's lots of methods here that have been proposed in recent years that say transformers are better or Mamba is better. And we found like pitfalls in their validation, like using extra training data and not talking about it, or using extra residual connections that the baseline didn't have, and so on. So if you're interested in this, you should read the paper. It's called NNUnit Revisited. Yeah, and so this is, as a disclaimer, this is on the current data sets that we have, right? That are a few hundred images. Now when we talk about thousands or millions of images that we train on, we will maybe see benefits of transformers, right? But at least with the current benchmarks, we don't. And so the last point that I wanna make is how to reliably track process. I talked about this before, right? The AlphaFold advice that we got. And so how can we make sure that we're solving the right metric, that we are on the right track with the right benchmark? We developed this nice scheme to say how good is a data set for our purpose, right? We see a lot of cherry picking of different data sets. There's a lot of data sets in the domain, and you can't just pick the data set that shows that your method is the best, right? How do we prevent this? And so we have this quality score for data sets now. How do you measure the quality of a data set? Our suggestion is that we say 2 criteria. 1, we want to have a low intra-method variability. That means you apply the same method to your data set several times, then you want stable results, right? That means that there's not a lot of statistical noise, right? It's a robust data set. And at the same time, you want high inter-method variability. That means you have 10 methods and you apply them to the same data set, you want to see differences in the scores, right? If they all have the same score, then your data set is saturated and you don't get a good signal for which method actually works best, right? And then between these two numbers, we can build the ratio, that's the quality score, or we can plot it in 2 dimensions, and you see that half of the current most popular benchmarks are sort of in the red area, so you can't really get a good signal for which method works better out of these. Right, okay, so this is the last slide. I thought instead of a summary of what you've already seen, I just give you sort of my main learnings over the last years, what I think is really important to consider for research. And that's just my opinion, you might think differently. So with Think Big, I mean, not only like, yeah, I think if we as academia, I guess many of you are from the university, want to keep up with large, let's say, cooperative labs like Google and so on, we need to get away from small PhD student projects and sort of have larger collaborations, right? And it's hard in academia because if you want to do your PhD, in the end you need to show your own contributions and you need first authorships and so on. So I think we need a bit of a cultural shift towards lots of shared authorships so we can have bigger collaborations and bigger projects. Question everything. I mean, you've seen all the pitfalls that we saw, all the flawed validations in the fields that we worked on. So I think we also need a cultural shift in terms of being much more rigorous in how we validate our methods, right? So we need to value this validation more, and maybe even more than a new fancy method that sounds nice and has the latest buzzwords in it. That's very simple, simplicity over style. We saw with NNUnit that often the more simple method, if you execute it well, it works better than the too complicated and blown up method, even though it's harder to publish. And then maybe very obvious, but if you want to solve a domain problem, you should then integrate the domain people and the real experts from the ground up to sort of work together. And of course, don't forget to have fun. And with this, I close, and thank you very much for your attention. Thanks.